All right, settle down. So we'll look into the second sheet on geometrical optics, comprising some 18 problems, and I can almost presume that the enlightened bunch present here would have at least looked into the problems, right? All right. In any case, let's start with the first problem of optics sheet 2. So we have air, and then we have this glass, and then we have water, and then we have air. Water, you know, is 4/3, glass is 3/2 refractive index. And this angle is theta. So, we have a ray of light which is incident normally. At the air-glass interface, it goes undeviated. And then, glass-water interface is going from 1.5 to 1.33. That means from denser to rarer medium, it's going to bend away from the normal. Now, in this case, it's of course incident normally, so it will not undergo any deviation. I'm so sorry about this. It will not undergo any deviation. I'll just redraw this a little bit. I don't have room there. See, at this interface also it's incident normally, so it will go undeviated. It goes this way. And then, water glass interface, that means rarer to denser medium, is going to bend towards the normal. This is the normal at the point of incidence, it will bend towards the normal. Right? And then, glass air interface, it's again going to bend away from the normal. This is what happens, right? Now, if we want total internal reflection to occur at the glass air interface, that means if we don't want emergence at this interface, then we just got to make sure that the angle here is greater than or equal to the critical angle. That means if this angle, let's say, is beta, if this angle is beta, then we must have beta greater than or equal to theta c, where theta c is the critical angle between the glass air interface. Theta c is the critical angle between the glass air interface. And sine beta, therefore, greater than or equal to sine theta c. Theta c is the critical angle between, again, glass air interface. And sine theta c for glass air is going to be 1 by mu of glass with respect to air, that means 1 by 3/2, that is 2/3, right? So this should be greater than or equal to 2/3. Yes or no? Now, realize that if this angle is beta, this angle is also beta, alternate angles, right? And then this angle theta, this is 90 degrees, this is 90 minus theta, so again, this angle is theta. So then, at this point P, theta is the angle of incidence and beta is the angle of refraction. I can apply Snell's law at this point. That means mu of water into sine theta is mu of glass into sine beta, right? So we have 4/3. I'm applying Snell's law at P, 4/3 into sine theta equal to 3/2 into sine beta. Therefore, sine beta is 8/9 sine theta. Sine beta is 8/9 sine theta. So, right here, I replace this sine beta by 8/9 sine theta. So, we have sine theta greater than or equal to 3 by 4. Sin theta greater than or equal to 3 by 4. Such should be theta. Right? In order that the ray of light at the glass air interface is not able to emerge. Right? This is what should happen. Can I move on to the second problem? Second problem then? I told you in my last class, deviation through a thin prism, mu minus 1 into A. So this 4 degrees you can treat like a thin prism. In fact, again, how would you know whether a prism is thin or not? A thumb rule would be, let's say, on an average, anything less than 15 degrees or so, you can treat as a thin prism. Anything less than 15, 18 degrees, sometimes it could go as high as 18 degrees also, you can treat like a thin prism. And you can compute the deviation as mu minus 1 into A. Alright. So something like up to 18 degrees, you may want to treat the prism like a thin prism. So then, it's a thin prism. Let me just represent the effect of the prism by a thin entity of this kind. And this is the mirror. There is a ray of light which is incident on the prism and things happen inside the prism, and the net effect produced by the prism is a deviation of this kind. And the deviation produced by the prism is mu minus 1 into A, where the prism is thin, mu is given to be 3 by 2, so half into angle of the prism, that's given to be 4 degrees. So 2 degrees is the deviation produced on an incident ray. This is the emergent ray. This is the emergent ray, the final ray emerging out of the prism after having undergone 2 refractions. Alright, so I'm not representing what's happening inside the prism. It's not important for us. So the net effect is a 2 degree deviation. Net effect is a 2 degree deviation. Now, this then is also 2 degrees. This then is also 2 degrees. And this is the normal to the original position of the mirror M1. This is the normal to the original position of the mirror M1. The reflected ray is like this. This is the reflected ray. This angle is also 2 degrees, angle of incidence equal to angle of reflection. Now what is it that you are seeking? You are seeking the ray to go back to its original position. You want the ray to retrace its path. If you want the ray to retrace its path, then what you want is that this ray be incident normally on the new position of the mirror. Normally on the new position of the mirror. Which means you may want to have the new position of the mirror, something like this. This is what you want as the new position of the mirror. Call it M2. And in this new position of the mirror, this must be the normal. This must be the normal. So this is N1, normal to the original position of the mirror. This direction then is N2, the normal to the new position of the mirror. Yes or no? This direction of the incident ray should be along the normal to the new position of the mirror. That means the position M2. Is that right? Which means the extent to which you would want to rotate the mirror is the extent to which the normals rotate. The angle between the two positions of the mirror, this mirror and this mirror, would be the angle between the normals to the two mirrors. Right? This is N1, normal to the original position of the mirror. This is N2, normal to the final position of the mirror. And realize that the angle between the two normals is 2 degrees. So the angle between the two mirrors must also be 2 degrees. Therefore, the mirror ought to be rotated by 2 degrees in a clockwise sense as shown. So that it could retrace its path back. Clear? Shall we look into problem 3 then? Problem 3. So we have in problem 3 a glass slab we have a glass slab of thickness 10 centimeters and its farther side is silvered. This side is silvered. There is an object O. There is an object O placed 30 centimeters from the reflecting surface. 30 centimeters from this surface means 20 centimeters from this surface. Right? That's where the object O is placed. The image is found to be 23.2 centimeters behind the silvered face by an observer sitting in front of the block. That means the final image is found to be 23.2 centimeters behind the silvered face when an eye here is viewing all of it normally. Alright. In the process, we need to be able to find out the refractive index of glass. Okay. See, what really happens is, the ray of light that starts from O and gets refracted here, it will bend towards the normal, as you know. Rarer to denser medium, it will bend towards the normal. Right? And as far as the mirror is concerned, it seems the object is not at O, but is somewhere here. At O prime. At O prime. Where, again, you realize if this is 20, this must be mu times 20. The relationship between this length and this length would be separated by a factor mu. Since mu is greater than 1 and this length, as you can see, is larger, so this length must be 20 times mu. Now that I know this, let me just remove the clutter. I will not want to retain this. This will not be required anymore, right? So let me remove this. Let me just look at the length that would be required. So this would be 20 mu as far as the mirror is concerned. So for the plane mirror, the object distance is 10 plus 20 mu. Realize that? 10 plus 20 mu is the object distance. So the image of O prime form would be 10 plus 20 mu behind the mirror. Right? Means a ray of light like this, which gets reflected from this, seems like coming from point I prime. Seems like coming from a point I prime, which is 20 mu plus 10 behind the mirror, right? The object distance is 10 plus 20 mu. So the image distance with respect to the mirror must also be 10 plus 20 mu. Right? Now, eventually, denser to rarer medium. So the ray of light would bend away from the normal. Right? Denser to rarer medium, ray of light would bend away from the normal. And when it bends away from the normal, it seems like coming from I double prime. It seems like coming from I double prime, right? Bending away from the normal. And let's say this point is P. This point is P. We call this point Q. It's given that Pi double prime is 23.2 centimeters. That's given. Pi double prime is 23.2 centimeters. Now, as far as refraction on the final face is concerned, right? It's being viewed like this. As far as refraction from the final face is concerned, would you not believe that Qi double prime and Qi prime would be separated by a factor mu? See, as far as refraction from the final face is concerned, see, this is the ray which actually comes from I prime, but after refraction it seems to be coming from I double prime. That means this Qi double prime and Qi prime will be separated by a factor mu. And which one is larger? Qi prime is larger. Qi prime is larger. That means, can I say that Qi prime would be mu times Qi double prime? I could say this because Qi prime, from the figure, I can see that is larger than Qi double prime, right? But what's Qi prime? Qi prime is 10 plus 20 mu plus 10, right? So 20 plus 20 mu. So Qi prime is like 20 into 1 plus mu. That's Qi prime. See, 10 plus 20 mu plus 10 is 20 plus 20 mu. Saurabh? Nahi samajh mein aaya? Okay, 20, and then this must be mu times Qi double prime, which is 10 plus 23.2, 33.2, right? So we clearly have 13.2 mu equals 20, mu equals 5 by 3.3. 50 by 33. 50 by 33 is the mu, the refractive index of the material of the glass slab. For lens? No, that's for lenses. That's for lenses. And for thin lenses, no. Why? Well, in this case, first of all, this is thick enough. Those are for thin lenses. If there is refraction somewhere and you want to apply, so in that case also you can apply that when they are in contact. But then again, what focal length are you talking about when you are talking about this? No, I'll tell you what, that's a different situation. That formula that you're talking of, and I'm going to discuss that when several thin lenses are in contact and the last face is silver. I've not discussed that case, but that's not the one that would be relevant here at all. Right? No, not in this case. In this case, you can't apply that. Those are for thin lenses when in contact, when the last face is silvered. So that eventually the whole thing behaves either like a concave mirror or a convex mirror. The net effect of this combination would be like a concave mirror or convex mirror. I still have to discuss this. This is the only thing along with dispersion that I have to discuss in the class. Alright. So this I thought I'll discuss only after you get a hang of the basics of geometrical optics. Yes, that's this case. क्या चीज नहीं दिखता है, बिल्कुल नहीं दिखता है. This observer, see, what does an eye see? Eye see is the straight line path of a ray. बिल्कुल नहीं. It's only an intermediate formation. ये कभी actually form नहीं होता है. It's a virtual object. Because there are no, first of all, this is never the image. This is never the image. The final. Well, if it's an unknown material, then of course somebody would have to specify something in that regard as to how the rays of light. Otherwise, you can't say anything about this. See, even if that's not the case, eventually what you're going to do is you'll take the mu of this medium with respect to that medium. So now, then this will ray diagram aisa nahi hoga, but the equation will still be the same. Maybe the ray diagram will not be like this, but the equation will still be the same. Suppose this was larger than this, then this number would have been less than 1. So when you solve for mu, only the ray diagram will not be relevant, but the equations will still be relevant. Only the ray diagram will not be relevant, the equations will still be relevant. And when you solve for mu will turn out to be less. And that's when you realize and readjust your gears. okay, the ray diagram should then look like this. But the calculations will still be the same. So when you write your equations based on your ray diagram on the premise and assumption that one medium is denser and the other is rarer. But the equations, even if it was the other way around, would remain the same. I mean, this mu would be greater than 1, then this would be greater than this mu would be less than 1, that means this would be less than this. That would automatically emerge in the arithmetic involved. So it will not be a problem. There would be no loss of generality when you solve based on one understanding. Alright. So that's problem 3. Properly understood, right? So let's look at problem 4. So there is a plain mirror like this. And there is a ray of light, the incident ray. And it's incident at, let's say the grazing angle is 45 degrees. That's given in the problem. This ray of light goes this way. The reflected ray goes this way. Perpendicular, that is in the vertical direction. This is 45 degrees. And is incident on a thin prism. This is the thin prism. Whose angle is 4 degrees. Angle of the prism is 4 degrees. That means the deviation that it produces based on mu equal to 3 by 2, is 2 degrees, right? The deviation produced would be mu minus 1 into A, that's 2 degrees. So then, this ray of light so the net effect of the prism, after having suffered 2 refractions on the 2 surfaces, the net effect of the prism is an emergent ray like this. This is an emergent ray. And this angle is 2 degrees. Right? Now, the angle through which, now we want to rotate the mirror. So that the total deviation produced by the system is 90 degrees. Total deviation, that means in this case, see, the prism was not there and this was the ray. Then the deviation would have been 90 degrees. This is the original direction, this is the final direction. But in this case, what is the deviation? What's the deviation? See, the original direction is like this. This is the original direction of the original ray. This is the final direction of the emergent ray. So this 92 degrees is the deviation. But we want the final ray to be going this way. Such should be the rotation of the mirror. Okay. In any case, let's say when I rotate the mirror, I'm not showing the final position of the mirror. Nothing happens to the incident ray. Alright. The reflected ray from the mirror would get rotated. If the mirror is rotated by an angle theta, the reflected ray would get rotated by an angle 2 theta. Alright. So let me rotate the mirror by a certain angle so that the new position of the reflected ray is this, RR prime. The new position of the reflected ray is RR prime. Alright, by rotating the mirror by an angle theta, the new position of the reflected ray is RR prime, let's say. Now, it hits the prism like this, and again, the prism will produce the same amount of deviation, but what you want is, what is desired is, that the final ray be like this. You want the emergent ray to be like this. Yes or no? That's given in the problem. If the emergent ray is like this, incident ray is like this, then the deviation would be 90 degrees, right? So you want the final ray to be like this. Right? Now if you want the final ray to be like this, one thing, In the absence of the prism, this reflected ray would have gone in this direction, but now it goes in this direction. So the deviation produced is like a 2 degrees. It's 2 degrees, right? Evidently, this angle equals this angle. Why? Because this line is parallel to this line, corresponding angles. So this angle is 2 degrees, corresponding angles. Do you realize that? This angle equal to this angle, corresponding angles. Why? Because this is parallel to this. That means, by what amount has the reflected ray got rotated? 2 degrees. So, by what amount should the mirror be rotated? 1 degree, right. So, reflected ray gets rotated by 2 degrees or mirror by 1 degree. The mirror gets rotated by 1 degree. Sounds alright? Not a problem. So you may want to rotate the mirror by 1 degree for all of this to happen. Okay? Let's look at problem 5. So we have a lens. Whose algebraic focal length, let's say, is f. The sign is included in f, right? Algebraic focal length is f. When the object is at a distance u1 and u2, the image formed is real. And let's say the algebraic image distance is v1. v1 is along with its sign. It's not the magnitude of the image distance. Let's say it's the algebraic image distance. In the second case, if the object is at a distance u2, the image is formed at an algebraic image distance v2. This is a virtual image. It has to be formed on the same side as the object, right? That's a virtual image. Yes or no? And in both cases, the magnification is the same. That's given in the problem. Focal length, algebraic focal length is f only. Now, what's the magnification? Not v1 by u1, mod v1 by mod u1. I've always told you that magnification I will not treat algebraic. Right? So if I had said v1 by u1, then magnification would become negative because v1 is negative and u1 is positive. So magnification in our scheme of things will always be positive. So magnification is mod v1 divided by mod u1 in this case. What's the magnification in this case? Mod v2 by mod u2. You realize that v1 is negative. So mod v1 will be minus v1, right? And u1 anyways is positive, measured in a direction opposite to the direction of the incident ray. So u1 is positive and mod v2. v2 is positive, measured opposite to and u2 also is positive. So we have this as a consequence of identical magnification. We have this. Alright. We want to find the focal length of the lens. Now, for the first case, 1 by f would be 1 by v1 minus 1 by u1. Where the signs are already built into it in v1 and u1. And for the second case, 1 by f is 1 by v2 minus 1 by u2. Right? See, what I do is, I don't need v1 and v2. I need to find f in terms of u1 and u2. So this equation I multiply by u1 and this equation I multiply by u2. See, when I multiply this equation by u1, then I get u1 by f is u1 by v1 minus 1. When I multiply this equation by u2, then I get u2 by f is u2 by v2 minus 1. Now the way to eliminate is, if I add these two, then these two will vanish, because see, minus u1 by v1 would be minus u2 by v2. So if I add these, then this and this will get cancelled. Do you realize that? So if I add these two, I get 1 by f into u1 plus u2 equal to minus 2. Right? So that leads to f equal to minus of u1 plus u2 by. So that's the algebraic focal length. The magnitude of the focal length would be u1 plus u2 by 2. This is the algebraic focal length. It's coming tagged with that sign. So the magnitude of the focal length would be u1 plus u2 by. Clear? Clipটা change করে দে এবার একবার স্ট্যান্ড বাই দে problem 7 so I just repeat for the sake of recording problem 6 is on dispersion and the incident ray and the emergent ray, they are parallel to each other. When you draw the ray diagram, the incident ray and the emergent ray in problem 6 would be parallel to each other. There is no angular shift produced because of this system. In the absence of an angular deviation, there is no spectrum produced, there is no dispersion observed. That's what is going to happen. There would be no splitting of the ray, white light, into its constituent colors. White light would not get split into constituent colors if there is no angular deviation. If there is only a parallel shift, just like in a rectangular glass slab, there is no deviation observed. Right? So, let me move on to problem 7. When I do dispersion, you'll realize why this is the case. But problem 7. Just make a small note as far as problem 7 is concerned. Just make that should have been added in the problem. The angle of incidence 37 degrees mentioned. The angle of incidence 37 degrees mentioned is for the configuration shown. That is when the position of the mirror, is perpendicular to the wall. That is when the position of the mirror is perpendicular to the wall. That should have been an explicit mention of this. Otherwise, it's open-ended, the problem cannot be solved. You need to know what is the position of the mirror for this angle of incidence I to be 37 degrees. That's important. You'll realize when I solve this problem, you'll realize why that should be the case. Okay, so let's look into this problem with this revised change. Okay, problem 7. This is the mirror M, and that's the wall. This is an incident ray. This is the reflected ray. Let's say this angle is theta, and let's say this angle is alpha. By the way, this angle alpha I would always take not with the mirror. That's why I'm not saying theta equal to alpha, because this theta would change. This theta I'm treating as the angle between the incident ray and the mirror. This angle theta I'm treating as the angle between the incident ray and the mirror. But the mirror is rotating, right? Whereas this angle I'm treating as the angle between the reflected ray and the line perpendicular to the wall. Right? Now, the mirror is rotated at a speed 9 by pi revolutions per second. Is rotated at the speed omega equal to 9 by pi revolutions per second. 9 by pi revolutions per second, RPS. And revolutions per second means multiply by 2 pi, that will give you radians per second, right? Because each revolution is 2 pi radians. So multiply by 2 pi, so that's like 18 radians per second. That's like 18 radians per second. Now, realize that if the mirror is rotated by a certain angle, then the reflected ray is rotated by twice the angle. That means the angular speed of the reflected ray would be twice the angular speed of the mirror, right? The angular speed of the reflected ray would be twice the angular speed of the mirror. Yes or no? Now, to measure the angular speed of the reflected ray, the rate of change of this angle with time would measure the angular speed of the reflected ray, right? The rate of change of this angle with time would measure the angular speed of the reflected ray, yes or no? That means, can I not say that magnitude of d alpha dt, the magnitude of d alpha dt must be 36 radians per second? This is the angular speed of the reflected ray, 36 radians per second. And if the mirror is rotated this way for this configuration, then alpha is decreasing with time. So d alpha dt would be minus 36 radians per second, because alpha is decreasing with time, d alpha dt would be negative. So essentially, to be very strict, I can say along with the sign, d alpha dt is minus 36 radians per second. Right. Now, this length is given to be 10 meters. This length is given to be 10 meters. Alright. Let's say this height is h. This height is h. Now, the rate of change of h with time would measure the speed of the spot on the wall. The rate of change of h with time would measure the speed on the wall. Yes or no? For sure, h can be written as 10 tan alpha. 10 tan alpha. Right? So dh dt is 10 sec square alpha d alpha dt. In this case, realize that d alpha dt is minus 36. dh dt also turns out to be negative, which is what you expect, because if the mirror is rotated like this, the reflected ray is rotated like this, h is decreasing with time. So you would have expected dh dt to be negative. But what we are interested in is magnitude of dh dt, right? We are interested in the magnitude of dh dt, the speed of the spot on the wall. So the magnitude of dh dt would be this. And at what instant are we interested in this? At an instant when this angle is 37 degrees. At an instant when this angle is 37 degrees. And like I mentioned in the problem, this angle is 37 degrees for this position of the mirror. See, if this was not mentioned, then you don't know at what position of the mirror is the angle of incidence 37 degrees. then everything else would become junk, right? So when this is the position of the mirror, this is the angle of incidence 37 degrees, then this would be 53 degrees, right? In which case alpha would be 53 degrees for this position of the mirror, and cos 53 degrees is 3 by 5. Cos 53 degrees is 3 by, see, it could either have been 4 by 5 or 3 by 5, but over 45 degrees, it has, yes, it becomes less, cos becomes less than sine. So that's why 3 by 5. So then this becomes 10 into sec square 25 by 9 into magnitude of d alpha dt, which is 36 radians per second. So these many meters per second for 1000 meters per second. This is 1000 meters per second. Right? 1000 meters per second. So that was problem 7. That was problem 7. Let's look into problem 8 then. You have a question, Rana, that I can address? For problem 8, two plane mirrors inclined to each other with their reflecting faces making an acute angle alpha. A light ray is incident on one plane mirror. The total deviation produced after two successive reflections. I've derived this result for you. When n is even, when n is odd. When n is even, it's n times the angle, n times alpha, right? So it's independent of the angle of incidence and it's dependent on the angle between the mirrors. It's going to be 2 alpha. It's going to be 2 alpha. The deviation after two successive reflections is going to be 2 alpha. Here, it's independent of the angle of incidence but dependent on the angle between the mirror. I derived that result, right? N theta u. So 2 alpha is the answer for this. So option A is right, independent of the initial angle of incidence. Option D is right, dependent on the angle between the two mirrors. Alright. That was problem 8. Let's then look into problem 9. Let's look into problem 9. So far so good, right? There is an equiconvex lens, let's say, that means the radius of curvature of both the refracting surfaces is the same. Let's say R is the magnitude, not algebraic, R is the magnitude of the radius of curvature of each. It's just the magnitude of the radius, right? It's not algebraic. R is the magnitude of the radius. Radius of curvature of each face. Now, the lens, we need to check on the character of the lens, diverging, converging, and so on and so forth. When you want to check the character on the lens, you would then have to imagine rays of light coming from infinity incident on the lens, and after having suffered two refractions from the two surfaces of the curved surfaces of the lens, if the image distance, the image is negative, V is negative, then it's a converging lens. If V is positive, then it's a diverging lens. That's a check that we need to perform. Alright. So then, in any case, The incident ray coming from infinity. Incident ray coming out of infinity. Right? So object distance for refraction on the first surface is infinity. Right? The image formed by the first surface would serve as the object for the second surface. Right? An intermediate image, the image formed by this would serve as the object for the second surface. Yes or no? That's only an intermediate image, therefore. There is no actual formation of that image. So, when I apply refraction on the first surface, then I get image space refract. This is the image space because the ray of light is getting refracted into this medium, right? So, this is the image space N2 divided by image distance, algebraic image distance. So, let me call it V prime. That would be the intermediate image. And this would serve as the object for refraction on the second surface. So, image space refractive index by image distance minus object space refractive index is this, where the incident rays. Object space refractive index by object distance is infinity. Right? It's incorrect to write something like this. I would have directly written 0, but only for the sake of representation I am writing something wrong. You should not write n1 by infinity and stuff. So, in any case, image space refractive index by image distance minus object space refractive index by object distance is difference in the two refractive indices. Image space refractive index minus object space refractive, this minus this, divided by the algebraic radius of curvature. See, the center of this surface lies here. Center of this surface lies here. So, I am going to use a positive sign or a negative sign? Negative in the direction. So, should I use plus r or minus r? Minus r, because r is positive, minus r would be negative. So, minus r. Right? So, that's for n1, n2. That's for n1, n2. Now, this B prime, which is an intermediate image formed by the first refraction, serves as an object for second refraction between n2 and n3. Right? So, now, let me take refraction on the second surface. For the second surface, this becomes the image space and this becomes the object space because the incident ray lies here. The incident ray lies here, the refracted ray lies there. Alright. So, then I apply for refraction between this and this. Alright. So, image space is N3, image space refractive index by final image distance. Final image distance would be F because eventually, if the rays of light are parallel to the principal axis, then the final image would be formed as at the equivalent focal length of the system. So, image space refractive index by final image distance, which is F, the algebraic focal length minus object space refractive index divided by the object distance. Object distance would be V prime now, right? The image of this will now serve as the object for this. So, N2 by V prime equals difference in the two refractive indices N3 minus N2 divided by the algebraic radius of curvature. Now, the center of this lies here, measured opposite to the direction of the incident ray should be taken positive. So, should I take plus r or minus r? Plus r. V prime is only out of convenience. We may want to get rid of it by adding the two because we are interested only in the sign of f, right? So, when I add these two equations, I get like a n3 by f. This is 0, realize that, equals 1 by r into n3 minus n2 minus n2 minus n1. Right? That's n3 by f, which is 1 by r. R is a positive number. N1, N2, N3 are all positive numbers. Is like a N1 plus N3 minus 2N2. N1 plus N3 minus 2N2. Now, evidently, f would be greater than 0. F greater than 0 would cause it to be a converging lens. Would cause it to be a diverging lens. Right? Because then the focus lies here. The final image is formed here. Right? So, that's f greater than 0 measured opposite to that would cause the lens to be a diverging lens. Now, when is f greater than 0? F would be greater than 0 when n1 plus n3 greater than 2n2 That means N2 less than the arithmetic mean of N1 and N3. N2 less than the arithmetic mean of N1 and N3. So N2 less than the arithmetic mean, it will be a diverging lens. When N2 greater than N1 plus N3 by 2, the sign of F would change, F will become less than 0 and it will become a converging lens. Right? So based on whether N2 is greater than or less than the arithmetic mean of the surrounding medium, it will either be a diverging or a converging lens. Right? Let's look at problem 10 then. Can I wipe this off? You all okay with this? Sorry? Well, neither big, yes. If it's equal to the arithmetic mean, 1 by f would be 0, f would be infinity, there would be no deviation. It's going to go parallel. The final ray would be parallel to the initial ray. Yes, true. See? F will then turn out to be infinity. See, if N2 is N1 plus N3 by 2, then 1 by f would be 0, right? Because this turns out to be 0. That means f would be infinity. That means if there is a parallel ray, then after 2 refractions, it will still emerge parallel. See? Then after 2 refractions, it would go this way and then this way. The focus would be at infinity, right? So it will behave like a glass slab, rectangular glass slab. It will then behave like a rectangular glass slab. Rectangular glass slab mein, yes, parallel shift. There is only a parallel shift. Now, if you recall, while I was doing real depth, apparent depth kind of a situation, several layers of media on top of each other. This is T1, this is thickness T2, thickness Tn, refractive index mu1, mu2, mu3, mu n, and let's say this is the final medium mu m. And if there is an object O here, the bottom, then the shift in the object, that means the final image I, after all refractions and emerging into this medium, the vertical shift produced of an object would be the vertical shift produced by this, plus the vertical shift produced by this, plus the vertical shift produced by this. The vertical shift produced by this would be T in T1 into 1 minus 1 by mu of 1 with respect to m. That means mu1 by mu m, mu of 1 with respect to m, plus T2 into 1 minus 1 by mu of 2 with respect to m, plus Tn into 1 minus 1 by mu of n with respect to m, right? This is what we learned, where the refractive indices should be with respect to the emerging medium. If the emerging medium is 1, then these would be mu1, mu2, mu m, etc. Right? It's also possible that, let's say this was air, let's say there was air trapped here, okay, and if that was air, then this would be mu1 with respect to 1 would be 0, so then there would be no shift caused by this at all, right? If let's say if this was air and this was also air, or let's say if this was mu m and this was also mu m, then this would be 1 and this would be 0, and so on and so forth, right? So then we are ready to take problem 10. The object is at B. The object is at B. And there is an observer here. And we want the net shift to be 0. We want the ratio L by M to be such that the net shift is 0. So realize that we can imagine this entire layer as follows. There is x units of air, right? Let's say the point B is x units below this composite slab. So there is x units of air, right? Then there is, this length is M. So there is L minus M units of medium N1, right? And there is M units of medium N2. And then it's observed the final emergent medium is air, right? So the shift produced or perceived by an observer in this medium. Now this thickness is x into 1 minus 1 by mu of this medium with respect to this medium, which is 1. One, right, plus L minus M of medium N1, L minus M of medium N1, T into 1 minus 1 by N1, and then M units of medium N2, 1 minus 1 by N2, and we want this to be 0. We want this to be 0. It's independent of this x because this is 0, and you can divide throughout by m and solve for L by m. Divide throughout by m, so L by m minus 1 into this plus 1 minus 1 by n2 is 0. L by m can be solved for. You can solve for L by m from this by dividing throughout by m. Clear? No problem? Let's then look at problem 11. Let's then look at problem 11. Sumit, एक बार stand by था. Problem 11. Problem 11. Hey, if you recall one result, there is an observer in front of the mirror, halfway between a mirror and a wall. Anywhere, I mean in the vertical line, anywhere there is an observer O. Exactly halfway between a mirror and a wall. This is a mirror of size L. Then assuming that this is also A, halfway between the mirror and the wall, what he sees is a length, the patch on the wall that he sees in the mirror is 3 times L. I gave you this result in the class, right? It's 3 times L. Now the next problem is based exactly, and it does not matter where the observer is, he could be anywhere in this vertical direction. Does not matter. Does not matter where he is located. The next problem is based exactly on this result. So the patch that he sees on the wall is 3 times the length of the mirror. He is standing halfway between the mirror and the wall. Right? So we have a mirror of length L1 here, L, and another mirror of length L here. Separation between the mirrors is L. Separation between the mirrors is L. And the observer is here. Patch of light from this would be 3L. Because of the first mirror, it's going to be 3L, right? Because of the second mirror, again it's going to be 3L. Because of the second mirror, right? The patch because of the first mirror is going to be 3L. The patch he sees because of the second mirror is 3L. So this is not the portion that is visible, right? This is idling as far as the mirror is concerned. So from here to here, the total length that he sees is only 6L. Is only 6L, right? And time for which it's visible is 6L by U, because the speed of traversal of the man here is U. So the time for which he sees the wall is like 6L divided by U. 6L divided by U is the time for which he sees the wall. Clear? Let's look at problem 12. So that was problem 11 based straight on a result that we did in the class. Okay. Interference will not take place because of the geometry. There would be no common region. I know. That's why I drew the ray diagram for you. You can draw that and check for yourself. There would be no interference in the two patches. No, there won't be any interference between the two patches. There would be no common region in that 6L units. I know that's what we were poking at. Check on it. Now there is an object at a distance d1. This is roughly d2. The magnitude of the radius here is 60 centimeters. I1 is the image formed after all reflections and refractions. Now, what are the various things that happen here? There is a refraction on the curved surface. The image of this serves as the object for reflection here. So this will constitute an image. The image of this serves as the object for final refraction, and then the ray goes out of through. That's the final image, right? So 2 refractions, 1 refraction, right? That will constitute the final image. Now we are examining cases for which the object and the image coincide. Object and the image coincide. Geometrically, one possibility is if we had something like this going this way. Incident normally on the mirror, it would retrace its path and the final image would be formed at O, right? If that happens. So let me explore this possibility. Find the value of d1 for which a ray of light which is incident on this curved surface after refraction runs parallel to the principal axis of this unit, right? So if I apply, this is air, image space refractive index by image distance, etc. for the first refraction. Then we have image space refractive index by image distance. Image distance is infinity, right? If we want this image distance is infinity. Minus object space refractive index divided by object distances d1 measured opposite to the direction of the incident ray equals difference in the two refractive indices 3 by 2 minus 1, that is half, divided by the radius of curvature plus 60 or minus 60. Minus 60 because the center of this will lie here, measured in the direction of the incident ray, that's negative. So minus 60. Minus 60. So then D1 turns out to be 120 centimeters. D1 then turns out to be 120 centimeters. Right? So that's one way you can have the object and the image coincide. If you look at the options, so option A is correct for sure, irrespective of D2, and it does not depend on D2, realize that? So independent of D2, if D1 is 120 centimeters, the image and the object will certainly coincide. If you look at B, C, D, all these options are about D1 being 240, and the image still being formed at O, final image still being formed at O. That means, and all these options refer to, let's say D2, let's say at least B and C refer to D2. So it's worth examining what happens when D1 is 240. Technically, the image could also have been formed this way. Because of symmetry, you would realize that if this was the object distance, this is like this angle theta, this is the normal at the point of incidence. From symmetry, this angle theta, and then this happens. Realize, even then the object and the image could coincide. Realize that? Yeah. Now, which means if for refraction on the first surface, the image is formed at D2, then that would be a relevant D2. That would be a relevant D2 for which the object and the image would coincide. Right? For this object, if the image is formed at this point, then after refraction, the final image would be formed at O once again. Right? So let me see what happens. For refraction on the first surface, image space refractive index by image distance D2, positive or negative? Negative. So D2 is the magnitude, is actually the length. So I'll take minus D2 image space refractive index by algebraic image distance. D1 and D2 are magnitudes of these distances, right? Minus object space refractive index by object distance. Object distance is D1. Is difference in the two refractive indices half divided by the radius of curvature minus 60, right? Now, put D1 equal to 240. What is it that you get for D2? Put D1 equal to 240 and see what you get for D2. Hmm? 360? Right. Means if D1 is 240 and D2 is 360, then also this can happen. You got my point? Let's look at problem 13 then. Let's look at problem 13. Plane mirror. M1, M2. This is D. And let's say the magnitude of the focal length of this is F. F is the magnitude of the focal length of this. It's given that theta is small. We want the x and the y coordinates. This is the origin, this is the x-axis, this is the y-axis. We want the x and the y coordinates of the final image. We want the x and the y coordinates of the final image. Now, one thing that you can easily see here is that these rays of light getting reflected from the mirror, plane mirror. Let's say there is a ray of light which gets reflected from the plane mirror like this. This was the plane mirror. This angle was also theta for the mirror, right? Angle with the horizontal of the reflected ray. Right? This angle will also be theta, angle with the horizontal for the reflected ray. So this was a ray reflected from the plane mirror. This was a ray reflected from the plane mirror. As far as the concave mirror is concerned, then this angle will be theta. This is one of the incident rays on the concave mirror. This is one of the incident rays on the concave mirror. Now, essentially then, this concave mirror receives a parallel beam, but this parallel beam is not parallel to the principal axis. It will not converge to the focus on the principal axis, it will converge on the focal plane though. It will converge on the focal plane, right? These rays of light after reflection from the mirror, all these rays of light after reflection from the concave mirror let's say just take one of the rays, incident ray. After reflection, the image will form on the reflected ray. And where would the image be? The image would be, this is theta, this angle is theta, and this is the image, this is where, this is the focus, and this distance would be F. They will converge to some point I here. They would converge to some point I here, which is not the focus, but is in the focal plane, So, the image of this parallel beam is formed at I in the focal plane of the mirror, alright, such that this distance PQ would be F. PQ would be F, such that PQ would be F. It's not formed on the principal axis, it's formed away from the principal axis, but in the focal plane, at a distance from the mirror equal to the focal length. Clear? Now, realize that Qi would be F tan theta. Qi would be F tan theta, but theta is small and in radians, so tan theta can be replaced by theta. So this length is F theta. This length is F theta. This length is F theta, right? Now once you have this, Now think of this, although it's a point image, but you can imagine this to be an extended image. Imagine this to be an extended image of some object of size f theta placed at a distance f from the concave mirror and so on and so forth, right? Now, as far as the plane mirror is concerned, this is the plane mirror now. As far as the plane mirror is concerned, this Qi, this extended object Qi is at a distance d minus f. Is at a distance d minus f from the plane mirror. So for the plane mirror, for a second reflection on the plane mirror, this is the object. This is the object for reflection on the plane mirror. So then the image of this object Qi would be Qi prime, Q prime I prime would be the image. Q prime I prime would be the image of this object formed by the plane mirror, right? Such that object distance equal to image distance. So this length will still be d minus f. Call this point A. AQ prime would be d minus f. And this length will still be f theta. F theta. Object size is image size for a plane mirror. This is after 3 successive reflections, right? 1, 1, 2 and then 3. Pehla se to ye aaya. Second reflection this, and for third reflection this is the object, this is the reflecting entity, this is the final image. So and then it's given that this is the x-axis, this is the y-axis. So object distance x would be d minus f, y would be minus f theta. Y would be minus f theta. We are seeking this point actually. The coordinates of I prime, because I is really the object, we just imagined an extended object. I prime is really the image of the point object I. So y is minus f theta. Now, you might think I have kind of made life easier for myself by assuming that d is greater than f. Assuming d is greater than f. See, in this case, it seems like, I just assumed that this d is greater than f. What if d was less than f? You realize I've taken a special case only here. I've assumed d greater than f, but it's not given in the problem whether d is greater than f or smaller than f. You know what I'm saying? So let me quickly tell you two things. Number one, it will not make a difference even if d was less than f. First, two, let me draw a fresh ray diagram when d was less than f, what's going to happen. Alright, but for d greater than f, you realize these would be the coordinates of the final image. Not a problem, right? What if d was less than f? D was less than f. So again, we start with what the concave mirror receives. There are rays of light at an angle theta, inclined at an angle theta with the principal axis, and if there was no mirror, these rays of light would have liked to converge at some point I. If there was no plane mirror, suppose you suddenly remove the plane mirror, then rays of light that are incident on the concave mirror would have liked to converge to I, right? Where this angle is theta, this is f theta. Where this length is f, this length is, right? Now I am assuming that f is greater than d. That means, let's say the plane mirror is somewhere here. This distance is d. Right? So what would the plane mirror do? As far as the plane mirror is concerned, it would prevent the rays of light to come to this point. So this point then acts as a virtual object for the plane mirror. So if this acts as a virtual object for the plane mirror, see there is a converging beam converging at I, right? If that's a virtual object for the plane mirror, then the image of this object after reflection would be formed here, q prime I prime, where this length will still be f theta, this length will still be f theta, and this distance would be f minus d. This distance, right? This is f, this is d. This distance would be f minus d. So this distance will also be f minus d. This distance will also be f minus d, because this is the virtual object distance, real image distance for the plane mirror, right? So the final image is here, and this is the positive direction of the x-axis, this is the positive direction of the y-axis. So the x coordinate of I prime would be minus of f minus d, which is d minus f like before, and the y coordinate would be minus f theta. Y coordinate would be minus f theta. Sounds good? So it does not matter whether d was greater than f or d was less than f. The x and the y coordinates will have the same representation, right? D minus f and minus f theta. So let's look at problem 14. Let's look at problem 14. The distance between an object and its doubly magnified image by a concave mirror. Concave mirror, two possibilities, image real, image virtual. Although again let me tell you, the distance will still be the same, it will not depend on whether the image is real or virtual. But let's take both cases, image real, image virtual. So image real means, if this is the object at a distance u, its image I would be at a distance 2 times u. Its image I would be at a distance 2 times u, yes or no? Because the magnification is given to be 2, doubly magnified. So image distance would be twice the object distance, and real image means formed on the same side of the mirror, object and the image. So the distance between the object and the image would be u, and what would that be? Realize what's given in the problem is the focal length. That means 1 by f is 1 by 2u plus 1 by u, that is 3u by 2. Yes or no? So then we have 3 by 2u. So we have u equal to 3f by 2. U equal to 3f by 2. So realize that this length is also u. So the distance, isn't it? This is 2u, this is u. So the distance between the object and the image is u in this case, which is 3f by 2. So one thing for sure, 3f by 2 is certainly an answer when the image is real. The distance between the object and the image is 3f by 2 when the object is real. Let's see what happens when the object is virtual. When the image is virtual. Object O at a distance u, right? Image I at a distance, this distance would be 2u, not algebraic, magnitude. U is positive, this distance would be 2u. So in this case, the distance between the object and the image would be 3u, right? Where if I apply 1 by v plus 1 by u equal to, so in this case what is v? Minus 2u, right? U is positive, so V measured in the direction of the incident ray, because would be negative, isn't it? V would be minus 2U. So minus 1 by 2U, that is 1 by V plus 1 by U equals 1 by F. So 1 by 2U is 1 by F. U then is F by 2. And the distance between the object and the image is 3U. 3F by 2. Same distance. Same distance. So it didn't matter whether the image was real or virtual. 3F by 2 in both cases. Realize 3U. No problem? So let's look at problem 15. This is the object O. Image I. G2 greater than D1. And the image is magnified because D2 is greater than D1. And it's inverted, so it must be real. It's inverted, it must be real. The mirror must be a concave mirror. The mirror must be a concave mirror. And since it's magnified, image distance must be greater than the object distance, because D2 is greater than D1. So V has to be greater than U. Evidently, the mirror must be somewhere here. This must be the position of the mirror. So that the image distance is greater than the object distance. That will cause the image to be magnified, because D2 is greater than D1. And since it's inverted, it must be real, right? So that's the position of the mirror. Let's look at problem 16. Let's look at problem 16. Shall we proceed? Problem 16. An object is placed on the principal axis of a convex mirror. Of focal length 10 centimeters and at a distance 10 centimeters from the pole. X, let's say, which in this case is 10 centimeters. The object starts moving with a speed of 220 millimeters per second, that is 2 centimeters per second. At an angle of 30 degrees with the principal axis. At an angle of 30 degrees with the principal axis. What will be the speed of its image and direction with the principal axis at that instant? First of all, let me locate the image of O. At a distance y, let's say, at a distance, magnitude of image distance, let's say, is y. So 1 by v means minus 1 by y, right? Plus 1 by x, which is 10, that must be equal to minus 1 by 10. Y is the magnitude of the image distance. So 1 by v measured in the same direction as the incident ray. So minus y is what it should be. along with its sign. Plus 1 by u measured in this direction. So plus 1 by 10 is minus 1 by 10 because the focus of this lies in this direction, right? It's minus 1 by 10. So y then turns out to be 5 centimeters. Y then turns out to be 5 centimeters. Now, in general, let's say this is the velocity of the image. Velocity of the image making an angle theta, let's say, making an angle theta. When this is the velocity of the object, let's say this is the velocity of the image making an angle theta with the principal axis at such an instant of time. Now, in general, forget x is 10 and y is whatever. In general, when x and y are the magnitudes of the object distance and image distance, then I can say minus 1 by y plus 1 by x is 1 by the algebraic focal length. That could be said, right? Let me differentiate both sides with respect to time. Let me differentiate both sides with respect to time, right? Where x and y are the magnitudes of the object and the image distance for a virtual image formation here. Alright. So when I differentiate with respect to time, then I get 1 by y squared dy dt minus 1 by x squared dx dt is 0 because focal length is a constant. Even if x and y vary, f is not going to vary. That means dy dt is y by x whole square dx dt. Evidently, dx dt is 2 cos 30 degrees. Dx dt is 2 cos 30 degrees, horizontal component of the velocity. And y by x, y is 5, x is 10. So y by x is half. Y by x for that instant is half. So then dy dt then turns out to be 1/4 of dx dt. Dx dt is 2 cos 30 degrees. Right? So that makes it root 3 by 4. That's dy dt. Dy dt is what? Vi cos theta is Vi cos theta. So we have like a Vi cos theta is root 3 by 4. Other thing that you may want to imagine is, these components of the velocity would be would be the same as saying would be a measure of the magnification. If this is fixed, then this length is covered in a certain time. In that time, this length is covered. So it's like it will be a measure of the magnification. This velocity divided by this velocity will be a measure of the magnification of this system. See, in a given time, let's say forget this horizontal component. A certain distance is traversed. That means, let's say the object has traversed a certain distance. So imagine that the object has traveled 1 centimeter and think of this as an extended object like this 1 centimeter. What would be the image traversed? Something like this, that would be the extended image. You know what I'm saying? What I mean is the following. Can I just wipe this portion off? Forget the horizontal components, just the vertical components of the velocity. This is the mirror. In the vertical direction, the object travels a distance L1 in a certain time. Right? That means the object goes from O to, let's say, O prime. The image in the same time goes from I to I prime and travels a distance L2. Right? That means now you can also imagine the following. That this was an extended object this would be its extended image. You can imagine that? That means this length divided by this length would be a measure of magnification, but this length divided by this length is also the ratio of their vertical velocities. So the ratio of their vertical velocities would be the magnification, So then can I not say that Vi sin theta divided by 2 cos 30 degrees divided by 2 sin 30 degrees, 2 sin 30 degrees is y divided by x, the magnification, but y by x had turned out to be half. Y was 5 and x was 10, half. So then we have Vi sin theta as sin 30 degrees, which is half. If you square and add, you solve for Vi. If you divide, you get tan theta equal to something. So theta is known. Square and add, you get Vi. Divide, you get theta. Right? Right? Let's look into the next problem. Sounds alright? Problem 16 and problem 17. So we have a prism. Problem 17, we have a prism whose angle alpha is 1.8 degrees. Whose angle alpha is 1.8 degrees. Mu is 3 by 2. There is a concave mirror. Radius 20 centimeters. Alright. There is a parallel beam incident. This is the emergent ray, incident ray. This is the emergent ray. This was the original direction of the ray, right? The incident ray was in this direction. The emergent ray is like this. The emergent ray is like this. The deviation produced would be mu minus 1 into A. That means 0.9 degrees, right? Deviation is mu minus 1 into A. That is 0.9 degrees. This would have been the original direction. This is the actual final direction. So this is delta equal to 0.9 degrees. Now, if you imagine this ray, then this is a parallel beam coming from infinity. It will then settle in the focal plane. This distance would be f. See, there is a parallel beam coming from infinity onto the mirror. It will settle at a distance f from the mirror on at some point in the focal plane, like we saw earlier. Now this angle is delta. This is also delta. Now this is f. So what we need is the distance of the point from the principal axis, that is this distance where the rays will settle. Delta in radians, as you would see, is 0.9 into pi by 180. These many radians, right? That's delta in radians. So this distance x that we are seeking, x would be f into delta in radians. Tan delta is delta only when delta is in radians. So f is 10 centimeters, half the radius of curvature. So this is 10 centimeters into 0.9 into pi by 180. Pi is 3.14. pi by 20. Pi by 20. 0.157. 0.17 centimeters. Isn't it? 0.157 centimeters. Not a problem. It doesn't match with any one of the options. I have not made a calculation mistake, right? F 10 centimeters, 0.9 9 by 1 pi by 20, 0.157. It's not matching with any of the options. So next we have a wall flat mirror parallel to the wall. The light produced by a point source, the point source S, kept on the wall is reflected by the mirror and produces a patch on the wall. The mirror moves with the velocity v towards the wall. Now one thing that you would realize, let me look at the extreme rays, reflected rays from the extremes of the mirror, right? That's going to constitute the patch on the wall, right? This ray, for example, incident ray, this is the reflected ray, okay? So the image of S is formed at, let's say, S1. Image because of this is formed at S1. I mean, it's not the image, it's like yeah. Now, you realize that these two triangles are congruent. This is equal to this, 90 degrees, 90 degrees. In the event, let's say the mirror moves to this position. The mirror moves to this position after a while because it's moving up with a velocity v. The mirror moves to this position. Then the ray from this extreme, the incident ray at this extreme would be this. And again from congruence, do you realize that since this is equal to this, it will still go to S1. It will still go to S1. Realize that? This angle will still be equal to this angle. You can see that from geometry. That means if this is the incident ray, then the reflected ray will again settle at S1. So is there any change in S1? The patch produced, the point produced because of reflection here. Similarly, the point produced because of reflection here will remain the same, S2. So the length of the patch S1, S2 will not change just because the mirror is advancing towards the wall. It's going to remain the same. It's going to be a constant patch produced on the wall, changed neither in position nor in length. Right? Comfortable, na? Stand by the minute.